All right, welcome back to part 2 of the talk. Priyanka will continue.
Hello, good evening, everyone. Am I audible? Yes? Okay, so thank you very much to the organizers. I mean, thanks to the organizers getting this opportunity to share our work. It's great. Thank you so much. So, this technique is called loop abstraction followed by bounded model checking. So, we are going to look at a slide that Venki presented earlier. We are going to see it again. This is just to show the limitations of BMC. As you can see here, there is this program, which is a very simple program. And we don't know how many times it needs to be unwound for a bounded model checker to verify it. Yeah. So we know that BMC has been used very successfully in the industry also. And we want to use it now for verifying programs, even to prove properties where there are loops of large and unknown bounds. Okay? So that is the aim of this work that we are going to be presenting now. That is, in the presence of loops of large, unknown, and infinite bounds, we want to verify using BMC. We want to abstract it in a way that it can be verified using BMC. Okay? So what is needed for that? First, elimination of loops. Get rid of loops, because it's possible that BMC will be able to scale up for such programs. Yeah. And how we are going to do, and what is going to be the output of such is that we want to over approximate the behavior of the loops so that the outputs of the loop are over approximated. And in the abstraction, if the property specification, if the property holds in the abstraction, then it holds in the original program as well. So this is what we intend to do. Yeah. So we'll start with a very, very simple example. It's something called output abstraction. And this is aimed at eliminating loops. Yeah. So what happens here? It's a simple for loop where the variable I is initialized to 0, incremented in every iteration, and then it reaches a very large value, 100,001, or not. And the assertion is to check if the value of I is between 0 and 100,001 after the loop is over. So yeah, so we said that we are going to over approximate the outputs. So how are we going to do that? First, how do we get rid of the loop? So we non-deterministically assign a value to I. Yeah. So now it can have more values than whatever possible in the original program. And then we are going to assume the loop condition. That is, I is less than 100,001. And then we do an I++. So consider this to be the last iteration of the loop that is there in the program. So we are actually interested in reaching this point in the program where the assertion is, right? So we just want to get rid of the loop. So we are saying that we are accelerating to the last iteration. And what happens there is, if this is the last iteration, then the loop condition holds. And then this increment happens, that's the loop body. And then the loop condition doesn't hold anymore. Yeah. So no matter what value of I we start with, thanks to these two assumes at these points, this assertion can be validated. It's very simple. We don't need to actually analyze the execution of the loop, except for this much. Is that fine? Yeah. So if it's fine, then I'll move on. So this is what output abstraction is around. So now let's look at a more complex example, which also Venki showed on his slides, that there is a while loop which will be executed for as long as two variables np and npo are not equal. Yeah. So what happens is that in every iteration, NP and NPO are given the same value. But there is one block of code here which is executed conditionally where NP is incremented, and therefore NP and NPO are not the same anymore, and this loop goes on till whenever NP and NPO are same. Yeah. So if we had to perform such an abstraction as explained in the previous slide on this program, then what would happen? So we are saying that we are going to abstract the outputs of the loop, right? So what all is being modified in the loop has to be approximated. So what all is there? NP is being modified, NPO, R, because R is being assigned to GLB, GLB is being assigned to R, and then GLB also because it's being changed here. So we just have these variables, and then comes the loop condition, which is assumed. If this loop has to be entered into, then it is assumed at this point, and then the loop is executed, the loop body is executed, and then again it is assumed that the loop condition doesn't hold anymore, followed by the assertion. Yeah. So now again, see the play of this assumption, which is the loop condition. Since this is an abstraction, and since we have approximated these outputs of the loop, we are allowing it to execute, not execute this block of code in this iteration, in this body of the loop, right? Why? Because of this assumption that NP has to be equal to NPO whenever this loop is exit, and therefore this block of code cannot be executed anymore. Thus, only this will be executed, and we will be able to verify this property, that when this block of code is executed, state is L, and therefore state cannot be U, and therefore this property is verified. Yeah, so it's a very simple technique, but it is very useful as well. Yeah, so we just want to say that this is a very simple but very useful technique. And this eliminates loops. So this is one way of eliminating loops, by playing on predicates in the loops and havocing the outputs of the loops. So let me introduce some terminology now. Outputs of the loop. So consider this same example we'll take. There are different types of variables here. So one is the variable state, which is only modified and never read in the loop. Yeah. So let's call it a pure output because it's never read. Then there are these variables NPO, R, NP, and GLB. These are read as well as modified. These are read along paths, or their effect is seen in another iteration of the loop. After the current iteration, their effect impacts the execution of the loop later. So we call them inputs and outputs. We call them IO variables. And then there are some variables which are only read. So they are constants in the loop. They are not modified at all. And so we call them inputs. So this is the terminology. And the behavior of the outputs depends on the inputs as well as the IO variables, the pure inputs as well as IO variables. So now let us look at this example when we follow that method of eliminating the loop. So what we want to do is this. We want to introduce a bound to the loop. I mean, we can't every time havoc variables because it's not useful, and sometimes we can improve the precision by iterating over the loop a few number of times. How we do that is this. So this is what we did initially, havoc, and then assert, right, after this assumption. But we want to assign a bound. Is there a way to improve the precision? Is that you have to execute this exactly once, this loop exactly once. And why is that? Because there is exactly one pure output variable in this loop. Yeah, so what we are interested in doing is we are interested in giving values to variables which are never read in the program, which are only modified in the program. Yeah, otherwise we'll end up doing it for every output. So let's see. This is what we call an abstract loop. That removes large bounds and makes them into small bounds. Yeah. So what it is this. We iterate as many times what we did earlier. We do a non-dead to the IO variables, then we assume the loop condition and we execute the loop body. And we do it as many times as the number of outputs, pure outputs in the loop, or number of outputs in the loop. Yeah, why is that? So let us take this example. There is a simple do-while loop where there are two variables A and B being modified under some condition. Yeah, and we don't know how many times this will execute, but the property is that A can be either 10 or 20. Yeah. So now we just consider this execution of the loop. A general execution, we don't lose anything in this. We don't lose any generalization. We just check, we just say that in the first few iterations, let A be modified. And there would be some iteration of this loop where A is modified last, and it is never modified again. And then there would be some iteration where B is modified last and never modified again. So we are interested in that iteration, which is modifying A last, and we want to generate those values. We are interested only in those executions. And we want to abstract away the other iterations to reduce the bounds of the loop. Okay? So since there are only two variables which are being modified, we need two iterations for this loop. Okay? Does that make sense? So that's what this says, that we need to generate a value of A for A and a value for B. And that works. Let's see how that works. So suppose there are some n iterations of the original loop. So we want to map them all to some iterations of the abstract loop. And those iterations in the abstract loops are the ones which are going to generate a value of the outputs. And those outputs are as many as that are in the original loop. So that many iterations of the loop is what we need, of the abstraction is what we need. Yeah. So let's see here. Now there is one iteration, ijy, of the original loop in which read a set of values iojy minus 1. Okay, so there is some iteration jy of the original loop which got as input variables iojy minus 1, right? So these are the variables which are going to decide what path is taken through the loop body. Okay? And once we have the set of these values, then we just execute the loop body and then we can generate the outputs for this after this iteration, right? So this is what we do in our abstract loop, is that for that corresponding iteration in the abstraction, we just give a non-deterministically assigned value. We just assign non-deterministically all the IO variables. So then that abstraction allows the abstraction to execute that iteration of the corresponding iteration of the original loop, right? So it's an abstraction. And it can generate these values. And we want to do this for every output of the loop, right? So, so let's see how it is done. So we come back to the same example. And this is the example of the SLAM paper. What are the inputs of this loop? We already saw. One is the L variable and the second is the U variable, which are never modified, so they are constants. So we don't need to abstract them at all. Then the next are the IO variables, which are read as well as modified in the loop. So that's NPO, NP, and GLB. We are not considering R because R is modified first. So its value is always getting updated. So it's not a pure output. It's a pure output, not an IO. And then the pure outputs that we are interested in is state, which is only modified always, right? So as per what we said, the number of iterations required in the abstraction of this loop would be 4, would be 3. This is a typo. It would be 3 because there are, one second. The number of output variables is 4, counting R. So I've written 4 here, but it should be 3. But can we reduce it further? Okay, that comes later. So, so now this is the abstraction generated. Iterate 4 times with this loop condition. First, non-dead to these IO variables, which will decide the paths that are taken in the loop, or values which are assigned to variables. Assume the loop condition, execute the loop, then assume not of condition, and then assert the property. Yeah, so this is the important part. We've reduced the bounds of the loop in this abstraction. And this abstraction allows all executions of the original loop. So it's quite simple. So what we are doing is we are playing mostly with these assumes. We are taking advantage of, we are exploiting these assumes actually. And we are also abstracting the outputs of the loop. Now, we can shorten this bound further. You see, we can reduce it to 1. Why? Because there is exactly one pure output variable and there is exactly one block here. This block will always be executed, but this block of code is modifying this state variable. State is equal to u. So actually, if you can only execute this or not, that is sufficient for us to abstract all the outputs of the loop, because we are anyway abstracting IO variables through this non-dead. Yeah. So actually the number of abstract iterations needed is the minimum of the number of output variables or the number of blocks which are modifying pure output variables. So what we want to do, if there is this loop, and we want to allow abstract iterations in the abstraction which can execute blocks that assign to pure output variables. Because these pure output variables are something that cannot be, we have decided not to havoc. We are havocing only the IO variables, so they are getting abstracted anyway. These are not. So we want to ensure that in every iteration of the abstraction, some output, pure output, which is never read in the loop, is allowed to be abstracted. That's the idea. It's actually a very simple idea. Idea is iterate as many times as the number of blocks that modify outputs. And that is a very simple thing. You just have to count the number of blocks and the blocks that modify pure outputs. And you have reduced the number of iterations of the abstraction, and you've gotten rid of the loop in the program. Because usually this number is very small. And the idea behind retaining the body of the loop is that itself gives a good accuracy that acts as an invariant for us. We'll come to that. Yeah. So now let's come to the limitations of output abstraction. So far, it was easy for us because there was one variable which was being modified. Excuse me. And the assertion was on that variable. Now we have another variable in the loop, which is being modified. There is no condition on that variable, but the assertion is on that. And now, so if you just have a I as well as j, this assertion will be violated because there is no constraint on j. It can have any value, and this assertion will fail. So what to do in this case? Since there are no constraints in the original code on j, it will fail. So what to do in this case? So one way of doing that is if we knew how many times this loop will be iterated. If we knew that it would be iterated 100,000 times, then we could accelerate I as well as j, and automatically this assertion could be validated. It's a very simple technique, and it's called output acceleration, or it's just loop acceleration. And it automatically helps us. See, how it has been done is because I and j are accelerated equally and by an equal number of iterations, and therefore this assertion is validated. So hence now comes loop abstraction followed by bounded model checking. So it's a refined form of output abstraction. It reduces the bounds of the program just like output abstraction, but it is more precise. I mean, it gives better results. It is more practical, and it uses acceleration. It can handle conditions within loops also. So the previous program, you cannot accelerate. And firstly, you also need to compute the bounds. So what to do so that even without knowing the number of times that loop has to be iterated, the original loop will be iterated, how do you find closed forms, or how do you accelerate those variables without knowing it? Because it is a challenge to compute the number of iterations that each block or each variable would be incremented in. Yeah. So here we are going to present a very simple approach to that also. So in output abstraction, like we said, by doing some simple structural analysis, we were able to reduce the bounds. Now we'll do a similar structural analysis to find closed forms for acceleration. We also apply induction when the property is inside the loop body. So that makes it more precise. Right. So we studied various patterns of loops that occurred in the industrial code. And based on that, we came up with these type of assignments within loops. We'll go over them one by one. So clearly, you can see that output abstraction may or may not work depending on the property here. But so in this case, there is a non-recurrent variable. That means it's either assigned 10 or 20 and be done with it. It's a reset variable. It's reset to either 10 or 20. So in this case, how do we come up with the closed form? It's quite simple. X is either the initial value if none of these were executed, which is not the case here, but we don't analyze so much. So it's either the initial value, or it's 10, or it's 20. So whatever values the variable is being reset with, we just assign one of them, or it continues with the initial value. That's one closed form. It works well. Now this is the most important form and most useful form, is the self-recurrent form. You see, when this is the case where it is being incremented by, x is being incremented by 1 under some condition. Yeah? When there's acceleration, you don't expect there to be a condition here, but here we do. So what to do then? We say, let k1 be the number of times this statement is executed, right? And what would be the closed form in that case? X is equal to x0 plus 1 into k. So if k1 is the number of times this block of code was executed, this would be the closed form of x. And if we knew that x is less than or equal to 10, that would help us. But we don't. So what we do is that we say that, okay, let k be the number of times this loop is executed. K1 is is the number of times this statement is executed, and therefore k1 is less than or equal to k. So that makes it so much better. Yeah. And this is an abstraction. This is a loop invariant for this loop. So you see, by simple structural analysis, we are able to find the loop invariant. Right? Now, similarly, moving on to the next form is, this is the form we discussed earlier. This is self-recurrent along all paths. So this is simple. X is equal to x0 plus 1 into k, where k is the number of times this loop is executed, number of iterations of this loop. So this is simple, and this is precise, accurate. Right. So now coming to the example we had seen earlier. Remember, we were not able to prove the property over A. So here, now it would become that we don't need to know how many iterations this loop would require. We can just havoc that. And we can find closed forms for I and j, assume the not of loop condition, and we are done. What works here is that we know that I and j iterate an equal number of times. I mean, execute an equal number of times. These two statements execute an equal number of times. And therefore, we can derive this constraint for j as well, and the property holds. So it's a very simple way of abstracting loops. Yes. Now, then this is a special case where there is an if and an else. Yeah. So we know that the number of times this statement is executed plus the number of times this statement is executed is equal to the number of times all statements in this loop are executed. This loop is number of iterations of this loop. Yeah. So we introduce these three variables, and we just add this assumption, and this just makes the whole loop very much more precise, loop invariant. So what is it? X is equal to x0 plus 1 into k1 plus 2 into k2. So x would be the sum of this and this. Yeah, that's simple. And in this case, conditionally, this variable is being reset. So what would be the final value of this variable x? It would either be the initial value or 5, followed by a few number of times when this statement was, after this statement was executed. X is equal to 5 is executed. So this is also a simple closed form. It doesn't require anything special. And of course, for nonlinear things, we just have it, because we want our abstractions to be such that we can compute the closed forms easily. That's why we just havoc them. We don't want it to be expensive. We also don't want to get into Seaguard loops or refinements. So this is what we do. I just added this example to show how relations are also preserved across loops. So there are two loops, like the previous one. Here, k is being decremented and I is incremented up to n. And then there's a third variable which is introduced, and assertion is on the previous variable. And this program cannot be solved by any of the benchmarks in SVCOM that Venki demonstrated. And there are, so simple acceleration works in this case in preserving, and it preserves the relations between variables, and this program can be solved. Simple structural. Right. So this is the case when the assertion lies inside the loop body. We can also improve the abstraction by applying induction. So this is a special case of k-induction, wherein we apply abstract acceleration to all the IO variables. Yeah. So we have reduced the bounds, we have accelerated IO variables, assumed the property, and then asserted the property. So this is k-induction. For k iterations, we assume, and then we assert it. And this is the example where this is the base case. First, you prove that it holds for the base case. Then you accelerate, and then you assume it. And finally, you prove it. This really helps. This was another example from SV24, which we could prove using k-induction that no other tool could. Yeah, 18. They've removed it now, but it was there for quite so many years. You can say it is there in 23, 22. So, so this is a simple example, but it needs induction for it to be proved. You do acceleration, and then you see, since there is a break here, it's hard to verify this program. Now you can, after induction. Okay. Right. So we also use LabMC over industrial code, right? And that was the main aim, right? To show whether it can actually be applied and be useful. And if it could scale BMC. So we took a piece of code, which was a battery controller module from a vehicle, and it was 60 kilolines of code, right? The total number of loops were 272. And there were 186 assertions in the code. So what we did was we sliced the program with respect to these 186 assertions, yeah, just to improve the chances of scalability. Yeah. And then, so we got 186 slices, and the average number of loops, relevant loops in the slice, there were 50 loops in each slice, average. So that shows that there were a lot of loops in the program. And unknown bound loops were 25. Yeah. And yeah, we abstracted around 29 loops per program, per slice. And then we tried so many tools on it. We used CBMC. This was, of course, this work from 2015. So we used CBMC, LLBMC, and ESBMC. These were 3 state-of-the-art bounded model checkers at that time. We also used SATAPs for predicate abstraction to check how well it scales. Then Impara uses interpolation, and BLAST also uses predicate abstraction. So we used different techniques over these to check how well they perform. And you can clearly see the significant difference and the improvement. And these were actually alarms from static analysis that were generated by TCS ECA, which is a proprietary tool at TCS Research. Yeah, and we were checking the area index out of bounds property. So 10 minutes, we executed each model checker for 10 minutes and used Minisat. This was a very simple machine. We did it on some 8 GB RAM or something. And then we did some more applications. There were some 7 applications on which we tried. And here you can see the size of code goes up to 171.4 kilolines of code. These were also alarms generated by static analysis, only 8 GB of RAM. Yeah. And the properties are also several. Now, area index out of bounds, overflow, underflow, division by 0, right? So, yeah, only 4 cores for the last application with 4 GB of RAM. So there was, on an average, a reduction of 58%. The best was 69%, and the worst was 53. So it did pretty well there also. Oh, sorry, 27. So it did pretty well there also, and it did not take a lot of time to do all these, because here also we sliced the program, each property, into different slices, and we applied, in order to scale better, we did several other abstractions as well. I mean, we used to start from the leaf functions and go upwards in a way, in trying to verify the piece of code. Yeah, so this shows that it works in practice. And so finally, for this set of slides, I would like to conclude that it is useful to focus on loops for abstracting programs. Yeah, they are the main bottleneck. We should abstract them in a way that the abstractions without CGAR, in a way that can be used to verify properties. And this clearly shows that when there are paths without loops in program, then BMC can scale and can be used very nicely to verify to prove properties, not just verify, but also prove. We can avoid CGAR loops because that's very expensive. Even for simple properties where you can derive such loop invariance, you need not go into a CGAR loop, which is infinite. And you don't need to start with a very coarse abstraction. I mean, this way, where you just structurally analyze the program, you can come up with really useful loop invariance. So you don't need to start with a very coarse abstraction and then follow the wrong path down for refinement. Yeah. And we were able to find non-linear loop invariants, which were constrained by conditions in the loop, and that automatically makes the abstraction useful without having to come up with anything. It automatically happens that way. So that's why it's so useful. And we saw how it can relate variables across loops, and therefore it works on programs with up to 30 loops as well. And yeah, and we use very simple analysis. We use the AST CFG, of course, to figure out these types of variables, whether they were recurrent, non-recurrent, or all that. And we used flow sensitive or insensitive pointer analysis. So these are well-known techniques, and nothing great niche for coming up with these closed forms. But then it has its limitations. Venki already spoke about arrays. So it cannot prove properties which required quantification. And I mean, it works sometimes and sometimes it doesn't. Clearly, properties which need quantification will not work. Similarly, pointers, when it depends on your points to analysis. When a pointer will point to several locations, then you just don't know which value to accelerate with. The initial value could be one of the locations that the pointer is pointing to, so it could be really abstract and may not work. Similarly, resets, it's a weak point because sometimes you really need to know exactly which value flows out of the loop, and then you don't have it. And nested loops. When there are nested loops with a large number of paths, the abstraction itself will have so many iterations that BMC cannot scale anymore. So yeah, nested loops is a big challenge. Everyone is facing it and trying to improve. Although we have proposed some techniques, and it does work for a few nested loops also. We have tried it on industry code, but I won't be talking about it here. Yes, so that's all for this set of slides. Now we can move on to the next. I think time is fine. So if there are any questions.
What about the false negative? So your aim is to reduce the number of false negative or eliminate the false negative. I don't know which. So please let me know about the false negative, because you use the oversimplification. Yeah.
This one is a sound. The static analyzer is a sound one. Even our abstraction, it doesn't miss any alarms or bugs. So
Why?
why? Venki would be, I think, better to talk about Prism, which does not generate any false negatives.
I see.
Yeah, but Venki, you want to talk? Yeah, it's a sound. We have implemented sound techniques, so it doesn't miss any.
Yeah, it's a static analysis tool which implements sound abstract interpretation based, like interval analysis and.
So it can generate false alarms, but it doesn't miss. It doesn't miss bugs, but it does generate false alarms, which we try to reduce, but it doesn't miss bugs. It's sound.
What type of, you said you can also synthesize non-linear invariants with this.
Yeah.
What type of it did you?
So this is what I mean. These two together form an invariant. You see, in the loop, because this property holds before and after every iteration of the loop. So it becomes an loop invariant.
I see. But this is not truly, so it's a non-linear of what shape? This shape only, or is it even more complicated than?
So if you look at this one, resets. This is a slightly different, otherwise it's this shape only.
Right. And could you give some idea about how on nested loops this is useful at all, or?
It is actually, but we had to change it a little. We had to change the technique a little. Let me see. I can stop presenting. So, in nested loops, typically variables are read from the environment and then modified in the inner loop, and then read only in the inner loop. So we have attacked a specific class of such loops, reactive systems only. So there we were able to get rid of the outer loop completely. So it just became an abstraction of the inner loop. So it worked. So this was mainly focused on reactive systems, because outer loops only read variables and pass on to the inner loops. And we tried it on industrial code and it worked. I mean, it really helped BMC a lot. Let me see if I can find it.
No, that's okay. My question really is this a problem of BMC, or is it, I mean, so Are you innovating something on, translate? BMC already has problems with nested loops, right?
Yes,
So
yes.
is it a problem because of that you are inheriting, or is there something else you're able to do?
We are inheriting it because of that. So even though we are able to find bounds, there are loops where there are so many paths and they are nested. So you see, suppose the property lies inside the loop. Let me go to induction. Yeah, suppose the property lies inside the loop. So now we have a nested loop, right? So there would be a base case, which would be a nested loop. Then there would be a hypothesis, which would be a nested loop of small bounds, but still it's a nested loop. And finally, the check is also on a nested loop. So that's too many loops with, and if there are too many paths, we have reached up to 30 iterations for one loop, outer loop. And each outer loop will have an inner loop which is abstracted. So it becomes really big, it blows up. So it doesn't scale. Therefore, we got rid of the outer loop for such systems and then it scaled well. So shall we move on? Oh.
Because of reactive system, so you cannot apply loop flattening, right?
We can't apply?
Loop flattening. Nested loop can be a sort of single loop if not a non-reactive system.
Sorry,
Nested loop can be yes, smashed into a single loop. But this is this requires a loop cannot have a does not have any IO action.
Oh, when a variable doesn't have an IO, when a loop doesn't have an IO variable.
Yeah, so you have an IO variable.
Yeah.
Yeah. If there's no IO variable, so we can flatten the loops.
Yeah, yes, absolutely, because when there are no IO variables, life becomes very easy.
Yeah. Thank you.
Right. So now we'll move on to VeriAbs. VeriAbs is a portfolio-based verifier which uses all these techniques. It uses LabMC, it uses array abstractions. First, we'll see why. Venki touched upon it. We'll just go through once more. So in the industry, we obviously require a verifier which is accurate and scales up or verifies all programs. That is not practically possible. So I've just given examples here. Let's look at these examples also. So this is a program which requires array abstractions. Why? Because for all elements of A2 and A1, they are the same except for when I is equal to Z, which is coming from the environment. Yeah. So this is a quantified invariant, and so this requires array abstractions. The size of the array is also unknown, so it won't scale up using BMC. Now let's look at this program. I'm going through these examples because the properties of these programs play an important role in the later slides. So now this is another program in which, if you look carefully, A is initialized to 0. There's a loop which has unknown bounds. Then it reads an environmental input, which if that input is between 1 and 3, then A is assigned 3, else 5. And the property is on A. Now, this has an unknown bound, so even LabMC may not work on it because of it won't know whether A is to be 3 or 5. BMC definitely won't. What will work is explicit state model checking, because the number of states of this program are very few, very, very few. So if we can just identify it and use this, it would be very useful. Then there's this program, which is not verified by any tool from SVCOM. And there are around 30 tools in SVCOM. None of them can verify it. Is this property that I think Venki also showed this program. It requires simple acceleration because it's acceleration along all paths. It's a very simple program if looked at from the loop's perspective. And finally, there is another program which cannot be verified using loop acceleration because it has multiple if statements. Then it has a very large state space, so it cannot be verified using ESMC, and it doesn't have arrays. So, but there's another way to verify this program. If you could figure out which path in this loop is taken first, you see there's a pattern. It will execute this if first a few number of times, increment x that many times, then the path will change. It will execute this path a few number of times. And so we can use BMC here to figure out the number of iterations that it will follow this path and the number of iterations that will be done for this path. So that's loop path summarization. It's a paper that was presented in CAF. Yeah. It is also implemented in our tool. So that's why this technique is needed for this particular type of program. So clearly we see that here a new technique is needed for every program. And these are simple programs. These could be used, these could come very commonly. So that's why, what is the solution? You need a portfolio of techniques, right? So there could be arrays, pointers, quantifiers, loops, resets, whatever. You can have a portfolio of techniques, and you can decide which technique to select for a particular program. That's technique selection. Yeah. So your chances of selecting the right technique and then verifying it improves. So this is just to show how it looks. So here is a portfolio-based verifier, which has 4 techniques: array abstraction, loop abstraction, ESMC, that is explicit state model checking, loop path summarization. And now, whenever you're getting such a program, you have to decide that this doesn't contain arrays, so whether I should apply loop acceleration to it or path summarization. And then there is another program here, and you have to decide whether acceleration or summarization. So that's the thing. Because selecting the right technique is very important. If you select the wrong technique, you will not verify the program. That's the whole thing. Right? And of course, selecting the right portfolio is also very important, because the techniques in the portfolio must complement each other, and they should try to cover as big a class of programs as possible, so that you can verify as many programs as possible. And the technique selection algorithm should be efficient. All these requirements are there. So this is another representation. And useful tools, Mux and Verifolio, implement this technique selection. Yeah. So, so one thing is, for the programs we saw, if the program has single path loops, or if it has arrays, or if it has resets or multiple paths, you could decide to apply some technique or the other. Yeah. So selecting one of the techniques, and the result of the technique would be the result of the verifier. Yeah. It is practical and it has been used. But let's look at these 2 programs now. So these 2 programs are quite similar if you look at them. The first program has an array of very large bounds, of a very large size. And the values of the elements of that array are not initialized. We are iterating over the array, initializing it with 42. And then we are checking whether all elements of the array are equal to 42. It's a very simple program. Now here, so array abstractions work on it. Now here is another program which also goes to the elements of an array of, say, a large size, and it initializes it with some value. And then later, excuse me. And then later it is iterating over this loop, iterating over this array, and it is breaking in between, and it is just checking that the value of I is less than or equal to n for all executions. Now, for this, you don't really need an array abstraction. And it may not work also because of this break. So you need an abstract acceleration on this program. But these 2 programs are very similar, so it is difficult to select the right technique for this. Okay. So what do you do? So one way to approach it is that you select a strategy instead of a technique. What does that mean? For these two programs, for instance, you perform area abstractions followed by abstract acceleration. You run them in a time-bound manner, and one of the techniques may or may not. If the first technique doesn't succeed, the second one will succeed. It's like that. Yeah. Yeah, so you try a suitable technique, exit if the verification technique is successful, else you try the next technique. But it's quite hard to decide the order of those techniques. So that's the thing. I'll just give an example here for these programs. So you give an input. So for the techniques we saw earlier, you give an input. You first check if it has arrays. Yes, then you apply array abstraction. For this program, let's see. You apply array abstraction. If it generates an unknown, then you try the next technique. In this case, it will be verified, so you're done. But in this case, you're not sure. So you try the next technique. Is it a program with short ranges? No. So is there one path in the loop body? No. Wait. Yes. For this variable, there's exactly one path. So you try loop acceleration, and you have solved the program, this one. And now here is another program, the one we saw previously. It has multiple paths. So, so you're going to execute the same algorithm, and you may or may not reach this point. So the problem with strategies is that if they're too long, then it runs out of time, and you need to have the right techniques in the beginning. It's just to demonstrate that. So what is the other solution? You can have multiple strategies in your tool. So this is one. VeriAbs and CPSEC are examples of that, of tools with multiple strategies. So now, instead of trying one technique on a program with single path loops, you have a strategy of techniques for programs with single path loops. You have a strategy of techniques for array loops, variable resets, and so on. So now your chances of verifying the program have improved even more. Yeah. It's a challenge to come up with these strategies. How do you come up with them manually? Large amount of experimentation, domain expertise, heuristics. So that's how you come up with strategies. You can also use machine learning. It is an active field of research, and it is being done more often than earlier. Yeah. So first we'll talk about VeriAbs, which uses manually selected strategies, manually defined strategies. So it's a reachability verifier for C programs, and it uses strategy selection based on loop structures and input data. So it has exactly 4 strategies. So it uses unstructured loop as one, array loops, that means loops modifying arrays or reading arrays, and short input ranges, and remaining all, which we assume are numerical. So this strategy is defined for numerical loops, which are kind of acceleration, etc. So this is how it works. And it also does a slicing in the beginning. So if a program can be sliced, then slices are generated, and this whole strategy is applied on every slice of the program. And then it generates a result for every slice. If we find a slice with an error, then we know that the program is unsafe because of the type of slicing that it uses. And if all slices are safe, then the program is safe. But if any one slice generates an unknown, then we don't know what it is. This work is in collaboration with IIT Bombay and CMI. This is overall architecture of VeriAbs. Now, we are going to go into the details of VeriAbs architecture. So this is the detailed architecture of VeriAbs. Okay, so there is a slicer which is sliced, which slices C code. Then if it is sliced one by one, it goes to the strategy selection module. Every slice is then checked for unstructured goto loops. Yeah, unstructured loops are those loops which are formed by goto labels. And return, etc., backward edges, etc. So in that, we apply 1K induction as implemented in CPA checker. Then for the second strategy, this is the sequence of techniques we apply: pruning, shrinking, and difference in variance. difference invariance is also an induction-based technique, which will prove the property for the difference between two programs. That means if a property holds for k iterations, they prove whether it holds for k+1 iterations also for programs modifying arrays. And then we also applied this entire default strategy followed by that. Yeah, we'll come to the default strategy. Then, as we saw earlier, for programs with short input ranges, we apply explicit state model checking, loop invariant generation. Now, there are two loop invariant generation techniques here. One uses test data generation for finding invariance, and the second does an invariant generation from program syntax. Yeah. So, and then this is it. This is the strategy that we use for short input ranges. And finally, the default strategies. So remember, this is for numerical programs. So we apply a k-path interval analysis, abstract interpretation with the number of paths which are accurately preserved as 1 only. And then this input goes to loop abstraction, that is LabMC. It verifies using with or without induction. Then we apply loop summarization, that is finding paths of loops that are taken and the number of iterations. This also uses BMC. And then we use a k-path interval analysis, which is slightly more expensive with a much larger number of paths which are being tracked accurately. And then we apply bounded model checking, which is for finding bugs. And this is another form of k-induction, which is a LabMC-based k-induction. So we find invariance using a loop abstraction method, and we keep on unwinding until either we run out of time or we reach a maximum bound of 256. 256 is derived heuristically. Anyway, it is the last technique. So this is the detailed architecture of VeriAbs. Yeah. So notice here that all these techniques, yeah, so Venki already showed the slide. So all these techniques are taking static analysis as input. Most of these techniques are around loop abstraction, and they are using bounded model checking in the backend. And finally, we also apply bounded model checking for finding bugs. So what is happening in a sense is that first we are trying to prove the safety using loop abstraction techniques. Yeah. First we are trying to prove the safety, then we are trying to find errors, and finally, all techniques abstract loops. So what we are doing is that abstractions without refinements are being compensated for by using test generation and bounded model checking. That's what we are doing. This is just an example which shows how strategy selection is done in VeriAbs. I'm going to skip this slide. Yeah, and this is just a classification to show what all techniques are used to prove properties. So LabMC, abstract acceleration plus split case k-induction, and invariance from program behavior and syntax, as well as test generation are used. Using test generation are used to prove properties. For falsification, test generation by fuzzing, and these techniques can do both, proving as well as falsification. But the idea here mainly is that first we are trying to prove using loop abstraction techniques, and then we are trying to falsify using test generation or bounded model. That's the main idea. So the thing is that we are compensating for our abstractions without refinements using these precise techniques. Yeah. So this is the breakup of programs that were verified using VeriAbs in SVCom 2024 on read safety benchmarks. There were more than 11,000 benchmarks, and as you can see here, more than 50% programs were verified by LabMC. Yeah, and there are some programs which verify very few programs, but you need those techniques because no other technique can verify those programs. So you need those techniques in the portfolio. Then there is BMC that has verified 20%, ESMC 15%. So this shows that when used correctly, in the right time, in the right place, BMC and ESMC are so useful. We should continue to use them in the right place. And loop invariant generation also for 3% programs, which many of those programs were not verified by anyone else. And area abstractions 5%. Yeah. So these are, like I said, over 11K benchmarks, which are a large variety because they have been divided into 15 subcategories. So it's a very different variety of programs. And therefore, we need a large variety in our portfolio also for techniques. And these benchmarks are first validated by experts and then added to the repository. Yeah, so that's the point, that strategy selection enables a better utilization of the verification techniques. And it's a very simple solution for giving a better way to utilize our techniques, existing techniques. Yeah. So now this is a comparison of VeriAbs with the top 3 tools in SVCOM. So CPA Checker, which also uses a very large portfolio of techniques. It uses a diverse portfolio. So predicate abstraction, interpolation, value analysis with CGAR, data flow. It does K-induction. So it uses a very large portfolio. Then there's Ultimate Automizer, which also searches for different types. It searches for invariants using different strategies. And there's ESBMC, which is a very powerful bounded model checker. It also uses abstraction in the form of K-induction to find invariants and prove properties. So here also, you can see there are 627 programs that are not verified by any of these 3 tools that are verified by VeriAbs. So this clearly shows that loop abstractions are useful. Loop abstractions done like this are useful. Yeah. And why? Because see, pruning, loop abstraction, shrinking. These are forming the biggest chunk of techniques that are uniquely verified by VeriAbs. And the techniques that I said that they are using, interpolation, predicate abstraction, they cannot verify. They can't handle inductive invariance, for instance. So yeah, this is the role. Yeah. In fact, there are certain programs that are verified by our K-induction as implemented in CPA Checker and not verified by CPA Checker itself, because we have placed it in the right strategy. So, yeah. So here is the performance of VeriAbs from SVCOM 2017 to 22. It has won 4 gold medals from 19 to 22, and every year so many new benchmarks were added. So till 22 there were 5,400 benchmarks, and you can see here. So the number of tasks solved by VeriAbs is quite high. And every year, so many tasks were added. See, 2.36%, 8.8%, 17%. So the only thing problem with manually defined strategies is that they're not scalable in the long run. How many experiments can you perform to keep on defining strategies? So they're not scalable in the long run. So you need something else, and that is dynamically define these strategies using we use machine learning for it. So here comes VeriAbs L. So VeriAbs L is a reachability verifier that uses a similar flow process as VeriAbs, except for strategy selection, which is now replaced by strategy prediction. So it predicts verification strategies for a given input program. And it uses a neural network for that. And it uses Booleans as program features. Yeah? And these Booleans define the program syntax and semantics. So this is in flow with VeriAbs. So remember, VeriAbs was using features, was checking for things like what? Whether there are arrays modified in the programs, whether it has inputs of short input range, programs of short input ranges, things like that. So it uses such kind of features for identifying the strategy for a program, and uses the same portfolio, obviously. And it also performs slicing. Yeah, so this is VeriAbs L. Now I'm going to show a slide here. So like I said, that earlier there were only 4 strategies. Yeah, so it's a very small set of strategies to select from. machine learning gives us a very large set of strategies we can. So if n is the number of techniques in the portfolio, then it can allow us to select n factorial strategies, because you can just arrange in whatever way you want to. So, and we said so far we have been having strategy selection using Booleans which define the characteristics of a program. So we decided to have features, so many features, which are portfolio driven. So we decided to decide which feature to be there in the program based on the strengths and weaknesses of the tools, of the techniques in the portfolio. But it should be the strength of some techniques and not all. Because if it's a strength of all techniques, then it doesn't matter which technique you execute on that program. So some strengths of some and weaknesses of some. Yeah, so here is the list of techniques, list of features that are there in the portfolio. There's go-to loops, forward and backward edges. So this is the first strategy we said, unstructured. This corresponds to the unstructured strategy. Then array elements modified in loops. This is for selecting array abstraction techniques. Short input ranges for telling whether ESMC can be useful on them. Then constant assignments. This is for showing the weaknesses. So this will tell that LabMC may not be good on this. But on the other hand, ESMC can be good on this. So this is how we made the selections. Linear acceleration is a strong point of LabMC. So this is one thing. Similarly, linear operations. When there are linear operations, then BMC can scale better. So linear means we should try BMC. All variables in a loop are self-recurrent, then acceleration is the technique. And variables are mutually dependent. When variables are mutually dependent in a loop, then it becomes a weakness of loop abstraction techniques. So it's better not to try that. It's better to try BMC on it. Then non-linear operations in a loop. It's a weakness of BMC. It's a weakness of abstract interpretation techniques, like the one that we use, k-path interval analysis. So it's better to, so these are the weaknesses of some techniques. So idea is that of the techniques that we had in our portfolio, we knew about their strengths and weaknesses, and we decided to pick those strengths and weaknesses as the features for learning. And now we have many more features than what we had in VeriAbs. Yeah. And most of the features are related to loops. Yeah. There is for control flow as well. Bounds, of course, we have, and there's control flow patterns as well, like recursive programs. Their LabMC won't do well, so it's better to try BMC and so on and so forth, as well as for nested loops. Now, this is the overall architecture of VeriAbs L. So when a program P is given as input, it goes to the feature vector generation module, which extracts these features from the program, and that is fed to a neural network. The neural network will have the input layer where the number of nodes in the input layer is equal to the number of features of the program, Boolean features of the program. Then this is passed on to, there are actually two hidden layers in this. And finally, it is passed on to the output layer, which has the number of output nodes, which is equal to the number of techniques in the portfolio. So we use multi-class classification because we want to classify whether a technique can do it or not. What is the likelihood that a technique can verify the input program? So we use multi-class classification, and we use the softmax activation function. So what that does is that it generates a score, a likelihood that this particular technique, can verify a program or not. So L1 corresponds to technique 1, L2 corresponds to technique 2, and so on and so forth. Assume there are 10 techniques. There are 10 techniques or 11. Yeah. And then we sort these likelihoods of verification from highest to lowest. So the first technique now has the highest probability that likelihood that it will verify the program. And so in that order, we execute those techniques. So this becomes the strategy. This is how the strategy is generated. This is what is being done. So the input layer is equal to the number of, the nodes in the input layer is equal to the number of features. Middle layer. So we keep on halving. So we keep on halving the number of nodes. The total number of nodes in the middle layers is less than the input and output layers to avoid over and under approximation.
I was expecting a specific number.
Oh, okay. So let's see. This is, if this is 22, then the first hidden layer will be 11. Second would be 5, and last would be the number of techniques, so that would be 11.
And how many data points do you train on?
I'll come to that. Really? 550? Okay, and I'll quickly come. So, yeah, so then actually most of it is done. So, to answer your question, Ashutosh, we performed our experiments on SV24 using this data and compared it with VeriAbs. You can see there is a significant improvement over VeriAbs, as expected. The training data we took is from SVCOM 2022. So we took, so there are 12 subcategories in SVCOM 22. And so what we did was we picked as many benchmarks which would allow 1% of programs from every subcategory. So like we said, it has a variety of programs and they're divided into subcategories. So we picked 12% because there were 12 subcategories in SVCOM 22. And we tested on programs from SV24. Yeah. So the number of programs is 628 or 648 programs. So yeah, 648 programs. And we did it for 15 minutes, up to 15 minutes, just like SVCOM. And 64 GB RAM and 20 CPUs in a cloud. So VeriAbs verified 5% more programs than VeriAbs, and VeriAbs could, sorry, this is wrong. This should be VeriAbs L. VeriAbs L could verify in the first 3 techniques of the strategy, it could verify 66% of the programs. I think that shows the power of using portfolio-driven features, even though they are just Booleans, showing the presence or absence of some structure or some semantics in the program. Just showing the presence and absence. So it produced good strategies, whereas now VeriAbs tried 62% more techniques than VeriAbs L. So you can say how much, this shows how much more time VeriAbs took than VeriAbs L. And sorry, this should be programs, typos, sorry. So VeriAbs L verified 720 more programs than VeriAbs that VeriAbs could not, and VeriAbs verified 176 programs that VeriAbs L could not. This is mainly because we selected the training data randomly, and the data points did not have the technique needed to verify those programs, and so it could not verify those programs. It was a completely random selection. How much more time? Over? Okay, so then maybe I'll jump to this slide. Now there were 588 programs. Good question. Yes, actually, but those programs are very big.
Okay, like, yeah, an example would be great. Okay, but maybe offline.
Yeah, we can show you several examples. Actually, most of these examples are like that. These examples, which no one else could do, we are surprised that LabMC could work on them. They're really big programs. Thousands of them were added.
I mean, there must be something human is missing. So, I mean, we can be extracted out and maybe explain.
So, actually, that is what is interesting. So far, we have been doing well with those set of features. Even though we have added new techniques.
Okay.
Yes.
So, I mean, you can come up with a small artificial example in which L version is really working, and that illustrates why human is missing that.
Yeah. Yes.
Yeah.
Thanks. Yeah. So here, Now, these are all programs that VeriAbs as well as VeriAbs L did, verified in SVComp, and the top 3 tools did not. That is CPA Checker, Ultimate Automizer, and ESBMC. So here you can see half of those programs, more than half of those programs are pruning, LabMC, and shrinking. This is very similar to VeriAbs' performance also. And now coming to the performance on SV24. So VeriAbs L has won the gold medal last year as well as this year in SVComp. That's why I showed results of VeriAbs till only 22, because after that VeriAbs L came into picture and started winning. So we trained on 800 benchmarks from Reach Safety SVComp 23 for VeriAbs L. And we went into that. So there were 13 subcategories, and so we randomly picked 13% benchmarks. And with that, it could verify 78% programs. Of the programs that were added in SV24. So that's unseen data completely. But it could verify. I mean, that was very heartening for us to see these results. And it also verified 167 more unseen programs than VeriAbs. And before that, it had not verified more programs than VeriAbs. You see, the scores are calculated after normalization. So VeriAbs had actually verified more programs, but because of normalization, VeriAbs L had won the gold medal. But this year, it has not just crossed that gap, it has also additionally verified more programs. Yeah, and that's it from my side, I think. I would just like to conclude that a diverse set of techniques is important to verify a set of programs. Those techniques, it is useful when those techniques are loop abstraction oriented, using simple structural analysis. And we can avoid CGAR by compensating for it using bug finding techniques like test generation, BMC, and explicit state model checking. And finally, a combination of loop abstractions without CGAR and bug finding techniques is more powerful than state-of-the-art techniques and portfolios. Thank you very much. Thank you so much.
Thanks a lot. Unfortunately, I think we have to leave. One quick question. If there's a question, follow up. Okay.
So this, if you get this training, does it matter how big your neural network is, or did you try other methods like regression or trees, ensembles, and like this choice of AI model should be justified?
Yeah. The number of nodes in the hidden layers did matter. So we just came up with something which is advised, that it's better to not have more than the input and output layer in the hidden layer. That's what we did.
Do you have experiments to try with different sizes?
No. I mean, that was done long back. We don't have it on.
So you're not retraining every year?
We are retraining, but since the input and output layer is constant, so we are not, the number of techniques remained, and the number of features is also the same.
But data may have changed, right?
Data has changed, but we retrained, but we did not change the neural network.
Okay.
Yes.
So let's close the session for now.
Yes. Thank you.